This is part 2 of Chapter 6 of the Functional Programming tutorial. In Part 1 we considered filterable functors, starting from examples. We considered the syntax of the functor block, starting from the intuitive requirements that the if operations should satisfy. We derived the filter laws, and then we considered what types could be filterable or not filterable on examples. In this second part, we will look at the laws more in depth. And one motivation is that there are 4 laws. It's a lot of laws to remember. Each of them seems to be describing a different side of the filter function, a different property. There doesn't seem to be any obvious connection between these laws. But actually there is. We will find, by looking at what the filtering function does, with a bit of intuition, we can actually reduce the number of laws to 2, and we can find why these laws must be as they are. To begin, consider our intuition from the first part of the tutorial, which is that we considered a filterable type like this, or like this. And we notice that when a data item does not pass the filter condition, then the remaining data items are moved into a different part of the disjunction. But algebraically, this is similar to replacing this type with 1. So whatever data items do not pass the filter condition are going to be replaced with 1, with the unit type. And if you replace this with a unit type, what is left is a type 1 times t, which is isomorphic to this. So let us see if we can make this intuition more precise. What does it mean that we replace a data item of type A by a unit type? If we're given a functor, such as f of a, how can we replace this data item by 1 without breaking the type? Because the replacing cannot be just happening blindly. That would be changing the type of f of a, and we're not allowed to change it. The filter operation should keep the type unchanged. So the first question is, how do we replace this data item by 1? Can we make that more precise? And second, maybe we replace it by a different type, so then how do we transform that type back to f of a? So let us try to do this, and first we will note that we could replace data items by unit if instead of the type f of a, we had the type f of 1 plus a, in other words, f of option of a. And that type means that every time that the functor f contains a data item of type a, instead now it contains a disjunction. Either it will be a data item of type a, or it will be 1, the unit value. If we had this kind of type, then we could easily implement the step 1. Every time we look at a data item of this type, we see whether this is whether this is 1 or a. If it is 1, then it remains 1. If it is a and it does not pass the filter condition, we replace that by 1. And this replacement does not break the type, because this disjunction contains both the type A and the unit type. So, but how do we get this type out of this one? We can use a function actually very easily called inflate. I just call this function inflate. It transforms any functor into the functor type of option A, and it works by lifting this function into the functor. So this function, which is in Scala the sum type constructor, it takes a value of type A and returns a value of type option A. It just takes this value A and puts it into the right part of the disjunction. So this function exists obviously for any type A, and when we lift this function into the functor using the fmap, we get a function from f of A to f of 1 plus A. So that's the function we want, that's inflate. So that always exists for any functor. And after that, we filter, so we perform the filtering operation by taking each element of type 1 plus A and filtering it. And that is just a filter operation on an option. That operation is defined in the standard library. It is obviously easy to define. We have done it in the first part of the tutorial. We just filter the option with the given predicate P. So if the option was empty, it remains empty. If the option was non-empty and the predicate holds on that value X, then it remains non-empty, unchanged. Otherwise, it becomes empty. Now, so far, we have gotten this type, but we need f of A. How do we get from f of 1 plus A to f of A? So that's step 2. So actually, the filter does that. So somehow this function must be available. So I call this function deflate. Somehow for the filterable functor, this function must be available. Otherwise, the filter couldn't work like this. So this intuition tells us that perhaps we should be able to define a function deflate for the functor f, if the functor is filterable. And notice that the standard Scala library already has a function called Flatten, which works like this, of this type. It takes a sequence of option and returns a sequence. So this is exactly the same type signature as deflate, except for specific functor seq for the sequence. So sequence is filterable, as we know. So this suggests that actually being able to define deflate is necessary if a functor is filterable. So let's look at this diagram again to see how this works. So we expect that the filter function applied to a predicate P and a functor FA, functor value FA, first works by inflating to f of 1 plus A. Then we filter the option inside the functor, so we lift the filtering operation on the option to the functor using fmap. We get again f of 1 plus A, then we deflate that into FA. And so then we get a function from FA to FA. That's the type signature of filter of P. Just to remind you that filter of P is a function that is taking FA and returning FA. So let's try to express more formally filter through deflate. Now there is a composition here of inflate and this fmap. Inflate itself is defined as fmap. So we have fmap of sum composed with fmap of filter. So that's fmap of the composition of these two functions by the property of fmap. Now the composition of these two functions can be simplified. I call this BOP, Boolean option, Boolean to option. So we take filter P, which is a condition from A to Boolean, and we get a function from a to 1 plus a, from a to option a. So we kind of lift the Boolean predicate p into a function from a to option a. And this function works by checking that the predicate holds. If it does, we just return some of that x. Otherwise, we return none. So this is defined by this Scala code. Now, notice here we use a standard filter on an option, which is a very simple function, so we aren't really using this filter on some arbitrary functor f. We're using a very specific function, which is called filter on an option. We did not have to write the word filter here. We could have implemented this by hand. It's very easy. So this function, BOP, Boolean to option lifting, will be very convenient for us in what follows. So make sure you understand what it does and how it's defined. It transforms a predicate from a function a to Boolean to a function from a to option a. So then we see that this function is basically a composition of this and this. So therefore, we can simplify and express filter through deflate by saying that this composition is equal to, so composition of the first two is equal to f map of BOP, and the second one is deflate. And so basically we have a composition of f map BOP and deflate. And that's how we would have expressed filter if we had the function deflate. So deflate is assumed of this type signature from f1 plus a to fa. Just a short digression about notation here. Sometimes I write functions with parentheses and sometimes without parentheses. Now this is similar to mathematical notation like cosine of x, where we do not write parentheses when this expression is very short, but we do write parentheses when it's longer. For clarity, for example, cosine of a plus b, or some larger expression, we would write, of course, the parentheses, but if the expression is very short, we do not write parentheses. So similarly, we would use this notation. We would write BOP p or f map f, filter p, without parentheses. So to summarize this in the function type diagram, filter p is defined through deflate as a composition of f map BOP, so BOP is BOP p, so already applied to the filter condition p, is a function from a to 1 plus a. So we lift it to a functor, we get a function from fa to f1 plus a, and then we deflate. So as another reminder, my notation is that the composition works from left to right. So we apply first the function on the left, and then we apply the function on the right to the result. So just so that it is easier to read, easier to reason about, and easier to write on the diagram. So far, we have expressed filter through deflate, assuming that deflate existed. So actually we can also express deflate through filter. And when we do that, it will be interesting to note we will assume that law 4 holds. So here's how we can express deflate through filter. Well, it's very easy. The idea of deflate is that we have a functor of 1 plus a. Some of these 1 plus a's are empty, some of them are non-empty. We just want to filter out those that are empty. Only the non-empty ones have to be remaining. And then we will get a function, those that are non-empty. We will extract the value of type a out of them, and that will give us f of a. So how do we do that? Well, we can write code like this. So f of a is a value of type f of option a. We can first filter on the condition that the option is non-empty, and then we can map with the get function on the option. Now the get method is a partial function that takes only the right part of the disjunction and returns the x, but it is undefined on the left part of the disjunction. So the get is undefined on 1 plus 0. So it's a partial function, but it is safe to use this partial function after filter. That's our fourth law. We have filtered to the condition that all the option values that pass are non-empty, and so it is safe to use the partial function. Now in Scala code, if this were a sequence, I would have used the collect function and written the code like this. The collect function is functionally equivalent to this on sequences. But for arbitrary functor f, not necessarily having the collect method, we can just use the partial function. It's safe because of the filter property 4. So if law 4 holds, then we can define deflate through filter. So we have defined filter through deflate, and we have defined deflate through filter. This means they are computationally equivalent. This is a very important idea. These two functions are actually doing the same thing. If we have one of them, we can have the other. And these are equations. These are not just mappings, so to speak, from one to another. These are actually equations. So one function is equal to some combination of the other function with stuff. And the other function is also equal to some combination with the first function with stuff. So basically it means whenever you have one, you have the other, and they carry the same amount of information and the same amount of power. So if you are able to define filter for some function, functor, you can also define deflate and vice versa. We have seen that some functors are not filterable, so you cannot define filter. Therefore, you also are unable to define deflate for them. And so we could actually say that filterable functors are those that have deflate. And we could specify them by implementing deflate. And then we could derive the implementation of filter from the given implementation of deflate by a standard library function. So we could actually define a type class of filterable through deflate rather than through filter. It would be equivalent, as we have shown. We can express one through the other, provided that the laws hold, of course, but they must be formulated for deflate in that case, and then we need to check that they hold. So deflate is actually very useful because its type signature is so simple. It's a function from functor of option A to functor A. And because its type signature is so simple, we can easily verify that some functors are certainly not filterable. Here are some examples. Consider this functor. If I wanted to check if this functor is filterable, then in principle, I could try to implement filter for it and check the laws. And that would take me a while, perhaps. So let me see if I can write a deflate function. A deflate function would have mapped f1 plus a to fa. What is f1 plus a? It is this type. Now mapping f of 1 plus a to fa means I'm mapping this type to this type. So I have a function from this type to this type. This function cannot be implemented because the argument contains the unit part of the disjunction. if the argument is unit, I need to produce a value of this type, but I don't have any a's. All I have is a unit type. If I'm in any of these parts of the disjunction, maybe I can produce value of type A, but if I'm in this part of the disjunction, I don't have any values of A. In order to define a function from this type to this type, I'm required to define what happens with every element of the disjunction when it is given as an argument. And so I'm not able to map 1 to A, and I'm also not able to map 1 to A times A. Being able to map this is equivalent to having a selected element of type A. But I don't have that. I don't know what the type A is. If the type A were pointed, then I would have a selected element, and then I would have implemented this function by returning that selected element when I'm given the unit. So, example of a pointed type is option of int. The pointed value, the selected value, is none, the empty option. But in this example, A is a type parameter. We do not have any more information about A, so we do not know whether it is pointed. Therefore, we cannot implement this function 1 to A, and therefore we cannot implement this function. Since we cannot implement deflate, we could not possibly implement filter either, because, as we know, filter is expressed through deflate, like this. Another example is this functor. This functor is not filterable. How do we see that? If we wanted to implement deflate, then we would have to map f of 1 plus a to fa. F of 1 plus a is this, so we need to have a function of this type. How can we implement this function? Well, we have an int and we have this, we need an a. Well, we can put an int here and we can get 1 plus a. But we need to produce a value of type a, and we only have 1 plus a. So this function cannot be implemented for an arbitrary type a, for the same reason. What if its argument is the empty option, the part of the disjunction that is unit? Then we would have to produce some value of type a, but we don't have one. Therefore, it is not filterable. So the function deflate is easier to implement than filter, and easier to reason about than filter. It's very quick to see that you cannot map this to this, and therefore it is not filterable. Or it is also easy to see when you can. So let us continue to analyze the laws of filterable, and we notice that we were able to define deflate out of filter only by assuming that law 4 holds for filter. The interesting thing that we will find now is that if we define filter from deflate, law 4 will be satisfied automatically for filter. In other words, deflate only has 3 laws. This is a very interesting observation, and perhaps unexpected. Let me now show how this is derived. We will now derive and mathematically prove that when filter is defined through deflate, law 4 for filter is satisfied automatically. For convenience, we will be using this function a lot, so let's denote this with psi_p. Psi_p is a function that already is applied to the condition p, and its type is this. So this function already encapsulates the filtering functionality. If this value does not pass the condition, then it will be replaced by 1. If it does pass the condition, it will remain here. we can then write filter like this, much shorter. Let us now write law 4. In this notation, expressing filter through deflate, law 4 looks like this. It is the partial function law. So if we first filter, which is this composition, and then we apply a map with some function, it's the same as we first filter and then apply the partial function map, where the partial function is defined as the same function as f, except it's only legal to pass values that satisfy the condition p. Let us use this type diagram, the function type diagram, as I call them, to visualize this law. In the vertices of this diagram are types, and each edge of the diagram is labeled with the function that makes the transformation from this type to this type. So then it is easier to read this law. This law means that first we take the type FA. Notice that here in this law there is no space really to write the types of everything. So this law is convenient like this. If we already know the types, when we just need to manipulate things. But if we need to first understand the types, then this notation is too short. It's better to use a diagram notation. And on the diagram notation, we just write the same things, except we put all the types, intermediate and final, initial, and so on, types of everything. So we start with a value of type of A. The left-hand side of the equation transforms in the upper part of the diagram. First transforms through psi p, and we get f of 1 plus a, because psi p has this type signature. Then we deflate, we get fa, and then we map with function f. F maps a to b, f map f maps fa to fb. And the lower part of the diagram, similarly, first psi p, we get f1 plus a, and we deflate, we get fa. Then we f map with the partial f, and we get fb. And the law says that if you take a value here, you go the upper way, or you go the lower way, you get to the same value here always. And that's this equality. Again, a little remark about notation. So I'm writing f map f without parentheses here. The type signature of f map is curried, so it has the first argument f, and then there's a second argument which is fa. And so f map applied to f is a function from fa to fb. And I do not write parentheses here for clarity. So think about this notation as, again, similar to mathematical function like cosine x or sine x without parentheses. So think of this as one value, one expression, like cosine x. Alright, so we have formulated the law in terms of deflate. How do we show that this law holds? Now we are supposed to show this with no further assumptions, perhaps, about deflate. Well, actually that is not true. We cannot do this unless we know something about deflate. So one thing we notice is that this law is supposed to tell me that it is safe to map with a partial function. It will be the same as if I mapped with a total function, because I have filtered. So I filtered out the possibly illegal values for this partial function. But the filtering happens right here, far from fmap. So there's this deflate step in the middle. I have filtered here, then I deflate, and then I do fmap. Maybe I will be able to reason about it better if this fmap were close to psi p. Because this psi p contains the predicate p. This also contains the predicate p. So maybe I can reason about this if they're together. Psi is, by the way, it's itself an f-map of something. So if I put this f-map next to this psi p somehow, if I transform this expression into an expression where I have a composition of psi p and f-map of something, then perhaps I can easily reason about it, because then it will be f-map, composition with f-map, and then I can simplify everything and look at these functions and maybe get what I want. How do we interchange deflate and f-map in the two sides of this equation? Well, remember that we have a law 1, which interchanges f-map and filter. So filter now is expressed through deflate. So maybe if we put it right here instead of filter, we will have a law that interchanges f-map and deflate. Such a law is called usually naturality law. So let's express the old law 1, the filter is law 1, through deflate. We get this equation, which is now more difficult to understand without the type diagram. So I write the function type diagram here. It starts with fa. It first maps with a function a to b to fb. Then we apply the filtering function. We get f1 plus b, and we deflate that to fb. Now this deflate is parameterized by f and b, so it's a deflate for f1 plus b to fb. The right-hand side is the lower part of the diagram, which first maps with psi of composition f and p. Now, p goes from b to Boolean, so composition f and p goes from a to b to Boolean, so from a to Boolean. And psi of that goes from a to 1 plus a. From fa to f1 plus a. So first we get this, and this already incorporates filtering. Then we deflate, we get fa, and then we map fa to fb using the same function f as we used here. So here the filtering occurs first, and then fmap. Here the filtering occurs after fmap. That's the law, that we can interchange filtering and fmap. Now, we would like to transform this so that we can have a law that interchanges deflate and fmap. We almost have that, except we have this psi in the way. So can we simplify this, perhaps, somehow? Let's write it down. Fmap f, composition with psi, which is fmap of Bob p, is by the fmap composition law, it is this. So can we simplify this expression? We can. Actually, there is a property which the Bob function has, which looks like we can interchange Bob with some functions. So it's like a naturality law, except it isn't, because Bob is not a function that works with functors. Only those functions can have naturality laws. So it's kind of a similar law that interchanges the order of Bob and some functions. Here's the function type diagram for it. We start with some type A. We first map fa to b. We get a b. And we map with Bob. We get b1 plus b. So Bob maps from b to 1 plus b. It takes the Boolean predicate and makes it an option kind of predicate, option valued predicate. The second way, the right hand side is a lower part of the equation, is first we do the Bob, the filtering. We get 1 plus a, and then we map the function f. So we have to map 1 plus a to 1 plus b using f. F goes from a to b. So obviously we just lift f to the option functor. So we get a function 1 plus a to 1 plus b. So this is denoted like, I denoted it like this, is f map for the option functor. I write opt for brevity instead of option. I need to spend less space in my equations. So how can we verify that this property holds? Well, I have code actually. I have both symbolic derivation of this and the code that checks. So let's look at the code. So here is the definition of filter from deflate, and here's a definition from deflate from filter. And let me see where my BOP property is. BOP, yes, it's here. So let me first look at the BOP property, perhaps, since we were talking about this. So BOP is defined like this, and I also defined it as composition of apply and filter, just like we did in the slide. It's a composition of this and the filter. So I can write it down if I want, explicitly as a composition. We can check that this is the same function. Actually, I have a helper function that checks function equality, which I could have used here, but checking function equality means checking that for all arguments x and for all arguments p, it has two arguments, so BOP of px is equal to BOP of composition px. So now the law of naturality is that this must hold. So f is of type, let's say, t to a, and this is a to boolean. So this composition is of type, this composition is of type t to boolean, and this composition is of type t to 1 plus a, and that should be equal to that function from t to 1 plus a. So therefore, we take t to string, just to check it, a as int, and so then we write that f composition with BOP of p, so I'm just writing it straightforwardly here. Composition in Scala is and then, so f is applied and then this is applied. So BOP of p is a function, so BOP is already applied to p, and the result is again a function, which is of this type. That should be equal BOP of composition f and p, like this, and then, so composition with map of f on the option. Then I apply both of these functions to some x, so that I can check that the results are the same. And also I can check this law symbolically. Now, of course, the test passes, but it checks the law for certain values, maybe for 100 randomly chosen values. This is perhaps enough of an assurance that this is correct, but it is nice to be able to have a rigorous derivation, not just a numerical test. So how do we find a symbolic rigorous derivation? We transform the Scala code. So the easy way of doing this is to first replace these mathematical notations with specific Scala code that corresponds to them. For instance, f composition, f and then bop p means first we apply f to some x, and then we apply bop p to the result. And we put in a definition of bop p, which is sum.filter of p. Then we expand what filter means. Filter means if p of f of x, then sum f of x, else none. So that is the left-hand side. Let's call this expression 1. And the right-hand side is that this applied to some x. In Scala, that would be .map of f. And then we do the same thing, so we expand the bop into its definition. We expand the definition of filter, which is this for option. Then we put the map inside, so if this condition is true, then this dot map, else this dot map. Then we simplify this, because we can obviously see this is a non-empty option, so mapping it over f means we just put f inside. So that is the result of the right-hand side of the law, and this is expression 2. Obviously, expression 1 and 2 are identical. So in this way, we have proved this property, both using a test, numerically, so to speak, and mathematically rigorously. Using this property, we can now rewrite law 1, which was this, by interchanging this f and bop into, so f composition bop, f and then bop is bop and then f map f, so we put that in. Note here that we have now f map of bop and then f map of f. Now this f map is with respect to the option functor, and this f map is with respect to the f functor. That's why I use this superscript opt to make sure we don't get lost in different types. So this is a lifting of f into the option functor. So this is of type option A to option B. And then we f map that over to functor f. And then we get this part of the diagram, f of option A to f of option B through f map of f map f. So now we rewrite this left-hand side like this, and we write the right-hand side that already contained the f map of this bop of composition, which was here. F map, because psi is f map of bop, so this is f map of bop of composition. This is this. So now the left-hand side and the right-hand side contain this common prefix, and we can remove it, because our goal is to show that they are equal. We do not assume that they are equal, we need to show that they are equal. So if we show that they are equal without this prefix, then they will be equal with this prefix. So we can remove this prefix. Now we need to show that this holds, and that exactly looks like a law for deflate that we want. This is law 1 for deflate. Now we also want to show that this law is equivalent to the law 1 for filter. Then we would have to show it in the other direction. And then we have to reason about why we can remove this prefix, but let's just keep it aside. This prefix, by the way, is the only one that contains the filter condition P. And so this prefix should, it contains the arbitrary filter condition P. And so that's how we would prove equivalence of the laws. But at this point, we're not so interested in the equivalence of the laws for deflate, because deflate actually will not be so important in terms of checking its laws for us. But we could derive the laws for deflate. There will be 3 laws. From the first 3 laws of filter would follow the 3 laws of deflate. And so at this point we have derived the naturality law for deflate, which was our, so on the diagram it looks like this. We first map f1 plus a to f1 plus b. Then we deflate with respect to b, or we first deflate with respect to a, and then we map a to b. And that should be the same. So that's the naturality law. And having the naturality law for a function between functors means that it's a natural transformation. That's basically the definition of natural transformation. It's a transformation of one functor into another, such that the naturality law holds, that you can fmap before the transformation, or you can fmap after the transformation, and that's the same. So here's an example of implementing deflate. So suppose we take this functor, then we look at the type of f of 1 plus a, which would be this, just substituting 1 plus a here. Then we expand brackets, just like in school algebra. We expand brackets, and we are allowed to do this because of isomorphisms in the polynomial types. So then we have this type, this junction. And then we say, well, we need to map with deflate this into this. So let's see which parts of the disjunction we could map into which parts. Obviously, this, well, the unit we can map into unit and into nothing else. This we should probably map into this. And these things could be mapped into unit, all of them. So all of these could be mapped into unit. And that's fine, that's natural transformation. And that would have defined the collapsing filter that we considered in the first part of this tutorial. The filter that retains the 2 values only when both of them pass the filter. When even one of them doesn't pass the filter, both of them are removed and we get the empty container. So this would be an example of implementing deflate for this functor. So it is quite easy. The function has a very simple type signature. And this illustrates what natural transformations do. So in general, a natural transformation would map some container GA into some container HA. And what it does, it rearranges the data. It is not allowed to modify the values unless we know something about these types, but generally we don't. And so this is an arbitrary type. We're not allowed to change its value. We're allowed to rearrange the order of values or the disjunction part in which these values are held. And we're, of course, able to remove values or duplicate them. Also, we're allowed, but we're not allowed to inspect the type and do something type specific and so on. So same considerations as for a good implementation of functor, that we just look at the type and try to see how we can produce a new type with no changes to the values. Exactly the same considerations apply here. A natural transformation will not modify any values. It will just rearrange data in a container. So if you have a natural transformation between 2 containers, which you don't always have, but if you do have it, it means that data in this container can be somehow naturally rearranged with no changes to the data, just some erasing, maybe some duplicating, and some order changing. It can be rearranged and you get this type, this container. So if these two containers are in some sense sufficiently similar that this can be done, this rearrangement of data, then you have a natural transformation between these two functors. So we have found the law for deflate, which is this, which interchanges fmap and deflate. Now let's use this to show that law 4 holds. What is law 4 expressed via deflate? It is this. I'm repeating the type diagram from the slide before. Now we can use the naturality law, which is this, to interchange deflate and map in both sides of this equation. So when we do this, we get this equation. So we just interchanged, and now this f is next to this psi in both parts of the equation. So we can now omit this common suffix, the common part of the two equations, because we're interested in showing that this is true. So if we show that this is true without the composition with deflate, then it will also be true with that composition. And so then we expand the psi back into its definition, which was here. It's just the definition for brevity. And we get fmap of this equal to fmap of this. Now this is quite simple to check that this is true. Let's write out the Scala code for the left-hand side and the right-hand side. We see these two pieces of Scala code. I've corrected the Scala code here. So this function, this partial function, will be always safe because we are applying it after filtering on the condition p. And so any values x that this partial function will receive will be guaranteed to satisfy the condition p. This is because this is the law 4 for the option functor. And we need to verify that it holds for the option functor when we define this filter according to the usual way of defining the filter, according to the way we have assumed that we define it. So let me show the code that that demonstrates this. Let's see if I can find it. Let's see. Flight. Can't really find it so easily that this law holds. So let me just write it down. So why does it hold for option? Well, we have sum of x, filter p, fmap, a map, case x if p of x goes to x, or f of x. So what is sum x filter p? It is if p of x, sum x, else none. So how do we map this? Well, if it is none, then it is none. So we put a fmap, we put a map in here. So this is equal to that. So this code is evaluated like this, to this expression. So now, how do we do a map on a sum? Well, we have a non-empty option here, so we just put this x in there. Now, clearly this p of x holds, so this sum will be evaluated only if p of x holds. So then we don't need this condition. This condition will be satisfied by the way that if is compiled. So then we don't need to do all this, we just do f of x. And that is precisely sum of f of x filter p of x. Sorry, filter p. So this is law 4 for option, that we can map with function f. So this is sum of x filter p map f. So therefore, sum of x filter p map f. So therefore these two are equivalent. And so what do we find? We find that law 4 holds. This was the last equation that we needed to show, and we showed that this is the same code that is evaluated in the same way for all arguments. Therefore this holds, therefore law 4 holds. So we find that the law 4 for filter holds automatically if we define filter through deflate. So let me show you the example code that was there before, where I defined filter through deflate and deflate through filter. So I actually used functions to define that. So I define a function which is called filter from deflate, which is parameterized on a functor. And this function takes an argument, which is a deflate function, which is a function of this type. And it returns, so this takes the deflate as an argument and returns filter as an argument, as a value. So it returns as a value a function with the type necessary for filter. So you see, this is part of the power of functional programming. We can transform code, one function into another, by writing a function that transforms code. Well, we don't actually transform source code. We transform expressions algebraically or using other functions. But the point is that we define a function that performs this work. So that can be done with no restrictions. So this could be any type signature pretty much, as long as all the type parameters are defined up front in here. One limitation is that we cannot have further type parameters inside of this argument. So this limitation is sometimes quite serious, but often not. So this is our definition of filter from deflate, is the f map of BOP and then deflate. So it's exactly how we defined filter from deflate. F map BOP and then deflate. And we also define a function that takes a filter and returns a deflate. Now, instead of taking a filter function, I just wanted to save myself some typing, and I assumed that the functor f was from the filterable with filter type class, so that has a filter function. And then so how do these functions work? Well, I'm supposed to return this function. So I take p, which is this, and then I'm supposed to return this function. So this is the fmap bop and then deflate. All I need to do is to prepare this fmap properly. I need to do fmap on an option. So I use the implicit evidence value, which is this implicitly functor f. It has a map function which has this type signature. It has the first argument, which is functor f of a, and the second argument, which is function f. But I need these arguments in the opposite order. I need first the f, because I want fmap. I want a flipped map function. So I want to interchange these two arguments. So for this I use the flip function, which is defined in my common code like this. It takes a function from a to b to c and returns a function from b to a to c. And its code I leave for automatic implementation. So this is this flip function, and then I get the fmap for the types that I need, and then I just write more or less the mathematical notation. And here also I prepare an implicit functor instance, implicit functor evidence, and then once I get that evidence into the implicit scope, I can use the syntax foa.filter.map. If I don't have this, then .map would not compile on an FOA, because FOA is a filterable with filter. All we know about it is that it's filterable with filter, but that actually includes functor, and that's not automatic that it includes functor, and so we need to prepare this evidence. Other than that, this is the definition we had in the slides. We deflate is first we filter non-empty options, and then we get the values from the options. So this is a partial function, but it is safe here because it's after the filter. And as an example, we do the orders example from the first part of the tutorial. And then we just deflate from filter, actually takes no arguments, and filter from deflate takes arguments. So then I first obtain deflate from filter, then I obtain filter from that deflate, and then I check that that filter is the same as the previous one. So that's what is checked here. So that the filter is the same function as the filter obtained from deflate that was obtained from filter. So then it's showing me that it's really equivalent functions. Alright, well, that is so good, but still we have a bit of complication, because deflate seems to have a lot of laws, 3 laws. And notice we always have this deflate composed with psi, with this fmap of something. Always deflate is with fmap of something in front of it. So maybe this fmap of something, or this psi, and then deflate, maybe this composition is actually easier to handle. Let's look at the type signature of this composition. The type signature is actually interesting. It is going from FA, then we get this fmap, this psi, which is going from some a to some 1 plus b. So let's say this is a function. We get f1 plus b, and we deflate that, and we get fb. So actually the composition of fmap and deflate is a function from fa to fb that consumes this function f from a to 1 plus b. So let's call this fmapOption, or fmapopt for short. Now, the type signature of fmapopt is that it takes an argument of type from a to 1 plus b. And note, this argument already expresses filtering and mapping at the same time. So this function from a to 1 plus b expresses first that we check some condition on a, and for some a's we return empty option, and for some a's we return non-empty. And then we also map a to some b in some way. So this f combines filtering and mapping, and the result is a map from fa to fb. So deflation is already incorporated. So fmapf composed with deflate. That is the definition of fmapopt. And here's the type diagram for it. So from fa to fb, either directly through fmapopt, and this is how we define it. It's a composition of fmapf and deflate. Now, it's important to note that fmapopt and deflate are equivalent functions, because we can also define deflate through fmapopt. To do that, it's very easy. We just make this arrow identity. We say, let this a be actually the same as 1 plus b. So let's say this is actually 1 plus a, and this is also 1 plus a. We can do this because a and b are arbitrary, so we can set a equals 1 plus b if we want to. Then this will be identity. So this is an identity function. And then, obviously, deflate is equal to fmapopt applied to that identity function, because these two will then become equal. So since we can express one function through another and the second through the first, they are equivalent. These are equalities, so these are not some kind of mappings. So these functions are actually equal on all values. So now it's interesting to express the laws in terms of fmapopt. Now law 4 is already taken care of, so it's already automatically satisfied. We can express filter through fmapopt. This is actually quite short, because we have incorporated this fmap and deflate into one function. So I'm writing out all the type arguments here for clarity. So this fmapopt has actually 3 type arguments, the f and the types a and b. And so now filter is this kind of thing. So now how do we show that the laws hold? Well, we will show it now. Actually, well, we cannot show that the laws hold. We need to derive what the laws are for fmapopt. We need to express filter through fmapopt and substitute into the laws. So for example, let's look at this law. Well, in this law it's probably easy. We just have some naturality. This law looks interesting. So there's some Boolean conjunction here. So how will we deal with it? Well, we need a BOP of this to be able to do what we need. So we need to know what happens when BOP is applied to the conjunction of 2 predicates. How is that expressed through BOP of the 2 predicates alone, through BOP of P1 and BOP of P2? Well, it so happens that for the option, this is the code. So we need to take BOP P1, applied it to x, to x, and then to do a flat map on the resulting option with BOP P2. So that is maybe unexpected. Let's look at the code that shows, so here's, by the way, deflate from mapOption and mapOption from deflate, and again the checking that they are equivalent when we take one from the other. So let me explain this a little later, but let's look at the Boolean property of BOP, the conjunction property. So we can check this property by numerical test, or we can check it symbolically. So numerical test is that for any x, a BOP of this applied to x is the same as that formula, BOP of P1 of x, flat map BOP P2. Why is that? Well, so we can write out the code. The BOP is defined as sum.filter. So we have this code. Sum.filter means that since this is already an empty option, if P1 of x and P2 of x, then it's sum of x, else it's none. So that is the left-hand side. Let's call this expression 1. The right-hand side of the law is that we have BOP P1 of x flat map BOP P2. Now BOP P1 x is this expression. So now we need to flat map this with something. How do we flat map? Well, if the option is none, then the result is none. Now if it's not none, then we need to check if P2 applies, and then we still have a sum, otherwise we have none. So we have this code. If P1, then if P2, then sum, else none, else none. So obviously we only return sum of x when both conditions hold. And so that is equivalent to this, which is expression 2, and expression 1 and expression 2 are identical. So we see that flat map actually expresses the Boolean conjunction in some strange way. So this was the property that we needed. And actually this is very important. We will be using this a lot, this formula. So let's have a notation for it. So this is kind of a composition of BOP1 and BOP2, BOP P1 and BOP P2. Let's call them Q. So Q actually is a function from a to 1 plus b, and Q2 is a function from b to 1 plus c. And we can write this formula like this. Q1 of x will be option of b. We can flat map this with Q2 and get an option of c. And so the result is a function from a to option c. So this is a kind of composition, but the types of the functions are kind of twisted. So the usual composition would be if the types were a to b, b to c, and the result is of type a to c. But here, instead of a to b, we have a to 1 plus b, so option b. Here we have b to 1 plus c, and here we have a to 1 plus c. So every time the type of the function is twisted, there is something added to it on the right-hand side. But it's the same thing that's added every time. So it's some functor that is put on top of that. So this is called Kleisli composition. And the general case of the Kleisli composition is for some functor m, where you have a function from a to mb, from b to mc, and you compose these two functions and you get a function from a to mc. So you twist the type on the right hand side of the function by applying some functor m. In our case, the functor m is the option functor. So we just apply 1 plus a. So we twist with 1 plus a at the right-hand side. So in this tutorial, we will only be using this Kleisli composition with this functor, or as I said, twisting. The notation for that will be Kleisli opt, and I would use a diamond opt, diamond with subscript opt, to remind ourselves that we're only using this specific case. So we're not going to be using the general case in this tutorial, but the general case is extremely useful nevertheless, so that's why I wanted to mention it. So this is called the Kleisli composition. So we're using the Kleisli composition for the specific case of option. So this is the Kleisli opt composition. And interestingly, this composition has an identity element, which is a function of this type that returns the non-empty option. This function is an identity for this composition. So if you take this function and compose it with this operation, with any other function, you get that function. And so we will show now that the Kleisli composition operation is associative and it respects the Kleisli identity just as a normal composition would. So this is very interesting because it is a full analog of a normal composition of functions with identity function and associativity of composition. However, the types are twisted. So how come we can even do that? So the reason is they're twisted in this way. So this is a special kind of twisting that allows it to work. The option is a very special functor, and that's why it works. And let us now look at the code that shows how this all works. So we define the Kleisli opt composition, which is a function from A to option B, from B to option C, into A to option C. The code of this function is left for automatic implementation. We also define an implicit class for syntax so that we can say this, we can use this symbol to compose using the Kleisli opt composition law. So we just refer to that function. We define the identity, which is a function from A to option A. Again, this is left for automatic implementation. But this is basically sum.apply. So x goes to sum of x. Just so that we know what it is, but that's what it is going to be implemented. And then we check the laws. So we say, well, I have this now function equation utility, and that checks that functions are equal, just for brevity. So this is exactly like the associativity of composition, except I replace the composition symbol, the little circle, with this strange symbol. But that's the only difference. So this is the Kleisli composition, and it is associative. And also the identity. So identity on the left, composed with f is equal to f, and identity on the right, composed with f, is also equal to f. And I check that with various types, but also I can derive this symbolically. And deriving it symbolically is again a matter of writing out Scala code and transforming it as if you are evaluating. So I will leave this for you to look at. I will just go through the first few steps that are necessary. The important thing to make it easier, you could just do it brute force. You could just write out this code and check everything. But it's much easier and more visual if you decompose the function of this type into a pair of functions. One is the filter function, and the other is the transformation function. So remember that this function represents at once filtering and transformation. But it is easier to reason about it if you decompose them into filtering separately and transformation separately. So let me do that. Here is how I can define f is if I have p and q, and here's how I define p and q is if I have f. So they are equivalent. So I can define one through the other and the other through the first one. So then I note that the composition, the Kleisli opt composition, expresses Boolean conjunction. We have seen this before, but now I'd like to see this more explicitly. In fact, so what is the Kleisli composition of the two functions? Well, I transform the code in the same way I did before. I expand, then there's an if, then I put the flat map inside the if, and so on. And I find that the P and Q component of the composition is expressed like this. So P composition, the filter, is the Boolean conjunction of the two filters, except that the second filter has to be applied to the transformed value of x, because it could be a different type. And the Q functions are simply composed. So the transformations that are inside here are actually composed in the usual way. But the filter is composed using the Boolean conjunction. And so this is why the laws hold. Obviously, the laws will hold for Q, because the ordinary composition is associative and respects the identity. And by the way, the identity function is mapped into a filter that is identically true and a transformation that is identity. And so obviously then the filter will be an identity element for this, because this will be identically true and something that will be equal to that something, whether it's on the right hand side or on the left hand side. And identity and these laws hold. So it is for this reason that the laws hold. You're welcome to check in more detail all these calculations. And I would like to wrap up the previous topic, the transformation from one function to another, and just illustrate a Scala trick here. So I want to define the deflate function from this mapOption, and I want to define mapOption from deflate. However, I have a little trouble here doing this, and the trouble is I want to define a function deflate from mapOption, which takes an argument that is mapOption parameterized by A and parameterized by B, but A and B must be specifically chosen. So remember how I define it here. Deflate is defined through mapOption when I set one of the parameters to 1 plus A, another to A. Well, I could write B here instead of A, so it will be B, 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 B. So I could say, I set in the deflate, I set in the fmapopt, I set A to be equal to 1 plus B. So A must be option of B. But how do I express this in a function? mapOption is a function with this signature, but I need to set somehow the type A equal to the type option B, so that this is actually the same type and I can put identity in there. How do I do that? So I use for this the cats library, which contains a useful utility called is. So this is a type constructor, which is parameterized by two types. The Scala syntax allows me to write is in between A and option B, but you can see that is defined just as a type constructor with two type parameters. And is a class that holds evidence that this type is equal to that type. What does it mean to hold that evidence? It means you could, in using this value, you could transform this type to this type or backward with no computation. You could just map identically. So this evidence would not compile because you don't have the implicit value if these types are not equal when you actually call this function. So when you define the code of this function, you don't know what A and B are, and you say they must be equal, so you have evidence that they are equal. But when you actually call this function, which we will do below, you need to write the types correctly so that actually they are equal, and then it will compile. The implicit evidence will be found. So once you have this implicit evidence, so then you return this. You have for example, an x of type A, but A is option B. So how do you get an option B out of it? Well, you use this coerce function, which takes an A and returns an option B in this case. And this function is automatically defined, but only because you have the evidence that A is option B. And here's the substitute function that will transform f of option B into f of A. Now A is the same as option B, so this transformation actually doesn't do anything. It doesn't perform computations. It's very convenient. And flip means that you do it in the other direction. So substitute would do FA from F option B to FA. But without flip, it would go from FA to F option B. So with this evidence, you can easily coerce one type into another, or the second to the first, and also with any functors. If you have a functor, and we do have a functor here, so we need actually to check the types and make sure that we're given FOB, which is of type f of option B, but we actually need f of A to call the function, and that's what we do here. So we substitute, which is a function defined for is, in the cats library, and it's very convenient. It's a bit of writing to get all these types correct, and actually all this performs no computation at all, because this is just identical equality of types. So x is just of this type or of that type at compile time. At runtime, it's actually the same value, because when you call this function, you must use the same types. So there's no or very little overhead in calling these functions. They don't actually perform computations. If you have a big data structure here, then this is immediate. This is very quick to do that. There's no computation. So how do we call that? So here's how we call that. We specify the types, option B and B. And then this is a type A, right? So this is a type parameter A in that function. And we specify it directly as option B. And that's why here as well, here we directly specify that, and that's why it compiles. So that's how we implement what's in the slide here. We call fmapopt with option B and B as type parameters. Here is option A and A. We'll just And we check that the deflate obtained by direct definition is equal to deflate that obtained through the mapOption, which itself was obtained from deflate. And just rename this for consistency. So these computations illustrate the equivalence between fmapOpt and deflate and the properties of the Kleisli composition. So let us look at the type signature of fmapOpt once again. It takes a function from a to 1 plus b, and it returns a function from fa to fb. In other words, we can imagine that we have this set of Kleisli functions, which are functions with this type, which is kind of twisted. So these are the Kleisli opt functions, or in the language of category theory, this is a function that belongs to the Kleisli category with opt functor. Now, for us, this is not particularly helpful right now. We are actually coming from another direction. We found that these functions were helpful, and we're studying their properties, and we discovered that they have this product, the composition of functions of this type, which is very similar to the usual function composition. And this function fmapOpt is very similar to a usual fmap because it lifts the function of this type into the functor, except for this twist. So it lifts a function from a to 1 plus b into a function fa to fb. Not f1 plus b, but fb. So this is a twisted kind of lift. But it's very similar to a usual fmap that lifts a function from a to b into a function from fa to fb. In other words, it lifts a computation into the functor context. It makes those computations occur on values that are held within a functor. So this is a very similar kind of lifting, although it's with a twist. This twist is, of course, highly non-trivial. We have a lot of work to do to deal with this, but once we have done this work, we see that this formulation is actually very intriguing. It's very similar to just lifting a function into a functor context. So, in fact, only two laws are necessary for this fmapOpt. Namely, this law that if you take identity function, then the lifting of that into the functor context gives you identity function on the functor, on the container. And second law is the composition law, which is that if you take the composition of two lifted functions, that's the same as the lifting of the Kleisli composition of these two functions. So let's look at the type diagram for the composition. We have fa, fb, and fc. So let's say f goes from a to 1 plus b, g goes from b to 1 plus c. Then the Kleisli composition of f and g goes from a to 1 plus c. And fmapOpt would lift each of them, but this lifting is consistent. So this way gives you the same value as this way. And that's the left-hand side, gives you the same value as the right-hand side. So the two laws for fmapOpt are very similar to the two functor laws. The two functor laws were that lifting an identity gives you identity, and lifting a function and composing it with another lifted function is the same as lifting of the composition. So they're very similar here, except that the types are more complicated. They're twisted. And as I said, and the composition here is a Kleisli composition. So this is some kind of twisted composition, and they're more complicated types than the functor laws, but conceptually they're simpler. Actually, they're also more complicated than the filter laws, but conceptually they're simpler. They're fewer and easier to understand. This is just some kind of twisted lifting from one kind of set of functions to another, and from functions of this type to functions on the container. And the lifting, of course, must respect the usual laws. It must lift identity to identity. It must lift composition to composition. So that's kind of natural. And there are no more laws. So they're only the natural laws for the functor, just twisted. So let us show that this is indeed so. I mean, I claimed so far, I didn't really show yet, that only two laws are actually necessary. Let me see how that is proved. So let's start with the law 3, which is the filter with the identically true function. Now, that function, after you bop it, it gives you this. And so this composition is the f-map-opt of the Kleisli identity, because actually the bop of this filter function is exactly the function that is the Kleisli identity. Is this function. Doesn't let me highlight correctly. This function. So therefore, if the filter law is true, then this is identity, and so then the f-map-opt of identity must be identity. And if this is true, then the filter must be identity. So the old law 3 is actually equivalent to the identity law. Both of them imply each other. So because of this equivalence, they're equal signs everywhere. So that's very strong identity. Isomorphism. Now, we need to derive the laws 1 and 2. Obviously, we have only one law, the composition law, left. And somehow this one law should cover two old laws at once. How can that be? So let's see. We know that the conjunction corresponds to the Kleisli composition. So the way that we can take one law and get two out of it is to use different type parameters in this law. You see, this law has 3 type parameters, A, B, and C. We can choose them to whatever we want. And choosing them in different ways can give us different, perhaps, specific laws. And that's what we shall do now. So let's consider Kleisli functions only of types A goes to 1 plus A. No other types. So we're choosing the type parameter in the Kleisli in this way. And then, actually, we can see that the filter composition is equal to this. So Q, I'm just defining for brevity that Q is bop of P. So all Q's are of this type. And then the filter is equal to f-map-opt of bop, right? So, in other words, f-map-opt of bop of P1, which is Q1, composition with f-map-opt Q2, that's the composition of two filters. Now, by the composition law, we have this, and then we know that the composition of the Kleisli corresponds to the bop of the Boolean conjunction. We have already derived that. So this derives the law 2. The law 1 is a little longer to derive because it's a naturality law. It has more stuff in it. it says that fmap can be interchanged with fmapopt. So notice that here we have specialized to functions of this type, the Kleisli functions of this type. Here we'll always also specialize, namely, we'll specialize to functions that are ordinary functions transformed into a Kleisli opt kind of function, which we will denote by kf. So kf is a function of a twisted type that corresponds to some function f of an ordinary type by always returning the non-empty option. So we just take a, we apply f to it, and always return the non-empty option. Never return empty option. So that is basically a composition of f with the identity in the Kleisli. And because of this, we have the property that fmapopt of kf is by definition is this. We can then decompose the fmap, because kf is a composition, so we can decompose that into fmap this and fmap of id. And fmap id on deflate is identity, because you can check that. And so yeah, let me think. Why I did not say anything here about why this is identity. So if you fmap the identity in the Kleisli, it means you map f of a into f of 1 plus a. But in that f of 1 plus a, there are no empty options, because the identity never produces an empty option. So then when you deflate that, there aren't any empty options, and so that returns you the original container. But in principle, this actually, that is actually easier. By definition, this is fmapopt of idopt, because this is fmap and then deflate is the same as fmapopt by definition. And so by the identity law, this is equal to identity. So therefore, this is equal to fmapf. So fmapopt of this transformed function is actually the same as fmapf. Therefore, we can just rewrite this law using fmapopt of kf instead of fmapf. When we do that, we can use the Kleisli composition. And so then, for example, we will get this using the Kleisli composition of kf and bop p, which we can then simplify, because we know that the kf times bop p we can just expand. We know that bop p has this law. It has the law that we derived before, this one. We know that bop p has this law, and so therefore we can transform this into that. The only thing we need to do is to see that if you do a Kleisli composition like this, then actually this is an ordinary composition with f. So all of this hinges on the fact that k was defined from an ordinary function f. So k is not an arbitrary Kleisli function. It's a Kleisli function that never returns empty option. And so it's much simpler to compose anything with it. You just compose normally, like this. And then finally you substitute that in there, and you find that this is equal to that. They're under fmapopts, and so therefore law 1 holds. I encourage you to go through this maybe slower, but all the steps are written here. We start with this, we rewrite, we define an arbitrary function f, then we define k out of that f, and we show that we can rewrite star as this equation. Then we show that what is under fmapopt is the same, by transforming the left-hand side into f and then BOP P, the right-hand side into BOP FP and then fmapOpt. So we just use, instead of Q here, we use this. Instead of Q here, we use this. And we obtain this property, which we already showed previously. So let me summarize what we have found. Filterable functors can be defined in different ways. We can define them using a filter function, using a deflate function, or using fmapOpt. All these three methods are equivalent. They're expressed identically through each other. And so if you have one of them, you can define two others. But these methods have different roles for us. In the program code, in the functor blocks, we use the if operation. And the easiest to reason about in the code is that operation, which corresponds to filter or withFilter. The type signature that is the simplest is that of deflate. That is the easiest both to implement and to reason about. Conceptually, however, the fmapOpt has the simplest laws. It has just two laws, which are functor laws with a twist. Now, let me talk a little about category theory. So, the two functor laws with a twist are accommodated by category theory as just some kind of generalized functor laws. In other words, as ordinary functor laws for some kind of a twisted functor. And the twisted functor has twisted function types. And so, if we, for example, look at type signatures of fmap, contra-fmap, and fmapOpt, compare them, you see this is an ordinary fmap type signature, this is the contra-fmap type signature, and this is the fmapOpt type signature. So they all look like some kind of lifting of functions from here into a functor context or container context. But this lifting is ordinary, and this lifting is from reversed functions, and this lifting is from these twisted Kleisli opt functions. Otherwise, it's very similar. The laws are the same, identity law and composition law. Now, here, of course, we have contra-composition, so the composition here goes into the other direction. That's natural, because we have twisted the composition, because we have twisted the type. Here the composition is the Kleisli composition, we have to twist it. So category theory says, let's consider all of them as actually functors, but on the left-hand side you have something twisted, so you have a twisted functor here. That's how category theory generalizes all of this into lifting. So it's always lifting from one kind of arrow to another kind of function arrow, to another kind of function arrow with twisted types. Now, category theory gives us intuitions about how better laws could be derived, and two of these intuitions we have seen is one is that it's probably helpful and useful if we look for type signatures that look like lifting. If we find a function like fmapOpt whose type signature looks like lifting, then it's probably very useful, because then you can expect that you just need to twist the composition here somehow of these strange twisted functions. Other than that, you have standard functor laws, just two laws, and they're standard. Very easy to understand. Identity and composition. So at the price of twisting the type here and using a different composition because the types are twisted. Second hint is look for natural transformations and use naturality law to interchange fmap and whatever you need. So you can do that, and that allows you to reason about the laws and derive one law from another. So that's kind of intuition. That natural transformations are useful because they have this naturality where you can flip fmap across them. And that is useful for deriving the laws. So notice how we have arrived at this place. We have started with filter. We derived a large number of laws, well, 4, okay, twice as many as now, a number of laws for filter. And then we were looking for a better type signature, basically, a smaller, more kind of reasonable type signature. Deflate had a great type signature, but fmap has fantastic, excuse me, fantastic type signature because it's a lifting. And its laws are very easy. However, category theory does not directly provide any derivations for these laws. So I don't think you'll find these laws in any category theory book. Filter and deflate are not usually found there, or the laws from them. Category theory is too abstract for that. It gives hints about what you could do, but it doesn't give you laws or equations for these functions or specific types. Doesn't tell you that this should have been the type that is at the root of being able to filter. That actually somehow you need to look for Kleisli and use the option to twist the Kleisli. Category theory doesn't tell you that. You start with filter and you think you're doing something very down to earth, filtering values out of sequences. And actually at the root of this, there is this twisted Kleisli opt category of functions. But category theory doesn't tell you that. You have to derive it yourself. It doesn't help you derive that either. It just gives you hints about how you might be able to do it. In particular, look for a lifting-like type signature. But we were lucky to find it. There's no easy way of deriving this. So what are the further directions that category theory hints about? I can give you 2 examples. So now that we have seen this pattern, let's investigate other kinds of liftings. For example, what if here I have some, I don't know, 1 plus a to b or something instead of this? What if I here have f of a to b instead of a to b? What if I have a to f of b with the same f as this? What if I have something else? What if I can try to investigate different kinds of liftings and see if they're interesting or useful. But this actually, so this is one kind of abstract direction we could go. No, I'm not going to go into that direction. I'll explain why. Another thing you can do is to replace the option in this construction by another functor. So not f, but let's say some m. And then let's see what happens then. We'll have some different twisted thing, and let's try to interpret it. So why I don't want to go into this direction is because, first of all, there's no end to different functions or types that you can write down. There's no end to twisting and generalizing and putting more functors here. You know, f of b of f of something. There is no obvious limit or obvious direction where to go. So infinitely many possibilities are open, and you can spend a very long time studying all of those possibilities with not much of a practical use. It takes a very long time to discover which are practical things that you can use and which are just theoretical things that don't necessarily give you a lot of practical value. So my approach is that I start with examples. I start with practical value that we obviously see in code, and then I generalize. So I generalize a certain to a certain extent, to a certain degree, and then stop. So certainly where to stop is a judgment call. There's no obvious decision to make. I mean, you need to understand, have some intuition about how much generalization is useful and how much is just idle play. You could go very far here in generalizing, and category theory especially encourages you to generalize with very little regard for practical use, and I don't think that's the direction I want to go. So, having said all this, let us look at the practical question. What are the filterable functors? If I give you some type, how do you know that this is a filterable functor? So let's, to answer that question, let's use intuition from our deflate type signature. So we reshuffle data in a container by replacing some values of type A by a unit, and reshuffling means we just reuse a different part of this junction usually, not always. So therefore we can try to reason about it and say, look at the type and try to substitute 1 plus A instead of A in the type and see if you can reshuffle the results to get FA again. If you cannot, it means you cannot implement deflate. I showed you examples of that, some simple ones, and then it's not filterable. But if you can, then you can look further how you want to make it filterable, and especially for your particular requirements of your application. And to get some intuition about this, let us consider how we can build up filterable functors from parts. This is very similar to what we did with ordinary functors. So we will now list some constructions, certainly not all possible constructions, but some sufficiently large number of constructions that give you new filterable functors given old ones. And let's see how that works. So first of all, a constant functor, meaning that for all types A, it's a constant, the same fixed type Z. And for that functor, we define fmapOpt as identity. So whatever type you have here, you can transform it from A to B, but Z stays the same. It's just identity. So filtering does nothing, and filter is identical constant, identical transformation, and Z is some fixed type. So that is filterable. Note that this is not filterable, the identity functor, for the reason that you cannot transform 1 plus A into A, unless A is a pointed type, but this needs to be for all types, so it is not filterable. The typical constructions that we have for functors are that you have a product of two functors, and that's a functor, same for filterable. Sum of two functors is a functor, same for filterable. Composition of any functor and the filterable functor is filterable. Now, this is not necessarily filterable, this has to be. So if you compose them, then it's filterable. This is a construction that's specific to filterables, and this is a functor that needs to be filterable already, and then you can do this and you again get a filterable functor. So notice we can replace this one with a pointed type, so we can do this. A pointed type is basically something that's that has an element that's selected somehow. So we could imagine that this is isomorphic to a disjunction of either you have that selected element, which is represented by this part of the disjunction, or you do not, or your value is not that selected value, and then you're in this part of the disjunction. So all the values that are not selected are in this type Z somehow defined, and the selected value is represented by this unit. So this is an isomorphism that you could imagine, not necessarily very useful as isomorphism, but you could imagine that this is 1 plus Z, and then this is 1 plus something. And so 1 plus something as a rule is filterable. Similarly, you could do many. So how do you filter this? If A passes, then you filter this, and you are still in the same part of the disjunction. If A does not pass, you return unit. You ignore that. You just drop all those values. A recursive filterable functor. We had an example where this was, I believe, a unit or something. But if G is filterable, then you can add this, and this is a recursive functor that looks like a list a little bit, except that the empty list is not empty, but this G. And then you have A, and then again A, and then again A, and then some G. So this is a list-like functor, and it is filterable in the same way that lists are. And the final construction is that you take some contrafunctor, which has to be filterable as well, and that function gives you filterable functor. Here's an example of something that's not filterable again. If you have even if this is filterable, this is not filterable, and so this entire thing is not filterable. So let us look at some of these constructions in detail and see how the laws can be satisfied. So take the construction of product. If the laws hold for the two functors, so they're both filterable, then let's do fmapOpt. How do we define fmapOpt for the product functor? So we have fmapOpt for the f and fmapOpt for the g. We have them, and now we need to define fmapOpt for fg. So we define that by taking the product of the two values, one of type fa, another of type ga, and we do fmapOpt on both of them separately. Obviously, that's an easy way of doing it. The identity law holds because it holds for the two fmapOpts, f and g, and therefore we have a product of identity of p and identity of q, that's p and q. The composition law holds because the composition acts separately on p and q, and so we have a composition of two fmapOpts f and two fmapOpts g separately. So these are, we are not mixing up p and q. So fmapOpt f only acts on p and fmapOpt g only acts on q. So we're not mixing it up, and so the composition acts separately on the two parts of the conjunction, on the product, and therefore the laws hold. Now we can transform each composition using its own law. This must be again diamond opt. I forgot the subscript here. And finally we get what the law for the product functor. Notice this is exactly the same proof as for the functor property. If you look at the chapter 4, we had the same construction for product of two functors being a functor, and the proof for the two laws of functor is exactly the same, except for the diamonds and these other notation, fmapOpt instead of fmap. Otherwise, it's exactly the same computation, 1-to-1. Why is this? It's because in category theory, fmapOpt corresponds to this generalized functor between a twisted Kleisli category, Kleisli opt category, which is kind of twisted, and the functions on the container. And so, because it is a functor, it has exactly the same properties of any functor. Once we define it that way, all the proofs remain literally the same, except for notation. New proofs, therefore, are necessary only when using non-filterable functors, when we cannot represent all the functors in our construction as filterable, which is constructions 4 to 6. In constructions 4 to 6, some functor is not filterable, like this one, and this one. And in this construction, for instance, they're both filterable, and so in the category theory formulation, that would be just functor. So that would be exactly the same proof as that this is a functor if this is a contrafunctor and this is a functor. So we don't really want to repeat the same proofs and just putting in some new diamonds and so on. We want to look at proofs for the new interesting properties. Here's the property that the laws hold for this type if they hold for GA. So how do we define the fmapOpt? fmapOpt acts on this disjunction. If the argument is in the right part of the disjunction of this form, then we return the right part, or if not only if the argument is in the right part of the disjunction, but also if the function f acting on A is in the right part of its disjunction. So this is, there are these two conditions. If these two conditions hold, then we return the right part of the disjunction, which is we return this B that was transformed from A, and we transform the Q using its own fmapOpt. Otherwise, we return the left part of the disjunction. So that is how we define the fmapOpt. Now, I remind you, fmapOpt takes a function that transforms and filters at the same time. So this function could give you the left part of the disjunction, the empty option, or it could give you a new B, new value. So if it gives you a new value, then and only then we'll return the right part of the disjunction with this new value, because we're supposed to return FB, so we need to return 1 plus B times GB, and so we return B times the fmapOpt in the G filterable functor. Now we check that identity law holds. It is straightforward. We take F in this definition to be the identity in the Kleisli opt category. So then I'm saying category just to get familiar with that terminology. All I mean here is that this is a function of type a to 1 plus a. I mean nothing else. And we know that functions of type a to 1 plus b have the property of this twisted composition, and they have this twisted identity. And that's all we know. That's what it means when I say it's Kleisli category. It's these functions of these funny types that have this funny composition. So taking f here to be the Kleisli identity, we find that f of a is by definition 0 plus a, by definition of this. And so fmapOpt of f is identity by the identity law in the G, that's supposed to hold. And if we put it in, then 1 goes to 1, and a times q goes into a times q. So that gives you identity. Composition law, we only need to check that if the argument is of this type, and only when all the functions return the right-hand side. Because if even one of the arguments in the composition returns the left-hand side anywhere, then the entire thing was going to return left-hand side, and then all laws will hold, because there will be none equals none in all laws. So the only non-trivial case that needs to be checked is that everything is in the right side of the disjunctions. In that case, the conjunction also is in the right side, and then we need to check what happens with this thing. And of course that's really easy, because everything is just working on this right-hand side. fmapOpt of this is by definition that, and we again apply fmapOpt, and we again have some C, which we assume that everything is in the right-hand side. Then we have composition of fmapOpts in the G filterable functor, and that has its own law, so we transform it like this, and finally we get the fmapOpt for f from the composition of the functions on the right side of the disjunction. So the interpretation of this filter is that it's kind of greedy. If A does not pass the test and all the data here is deleted, even if they all pass the test, the A is kind of very, very special, and only if the A passes the test, and we filter this and see if any of those pass the test. But if A does not pass, we return 1. So this is kind of a greedy filter. So now I've shown that its laws hold. Let me actually look at some code. Let's see if I have... Oh yeah, the Kleisli opt category, we have seen this. And yeah, this is implementing the filterable type class using the flatten instead of filter, and this is just the check that this is satisfying the law. So let me go to my worked examples for this chapter. So these examples show you that sums and products of filterables are filterable. So here I have an implicit def that produces an evidence for functor given the two functors f and g. So that is done using a type lambda here, and then I just do the maps on the functors in the usual way. The sum is the either, and I say that if I have f and g functors, and I have a functor instance for either fg, so that's trivial implementation here. And I do very similar, very trivial implementation using deflate. Very easy to do because of its type signature. And I show that if f and g are filterable and if they're functors at the same time, so it's the syntax in Scala is like this: colon filterable, colon functor. Then I have both evidence values. Then I produce a filterable for this type constructor, which is a type lambda, which is a product of f and g. And I do the same with the sum. So the implementation of deflate is particularly easy. I'm given a tuple of f option a, g option a. I'm supposed to return a tuple of f a, g a. And that's easy, I just deflate both of them separately. Similarly with the either, I'm given an either of f option a, g option a. I'm supposed to return an either of f a, g a, and I just match and deflate separately. And I can, why is this red? What did I change? Maybe I need to refresh this, because the tests passed. I check the laws, I have some data, and I use the orders. Now the orders 2 is the tuple of two orders, and orders E is the either of two orders. So I use the orders, and then the filterable instance for orders is already defined, and then I have already filterable for orders 2 and orders E. And here is the code for the construction of functor construction 5, where I have a functor G, which is filterable. So first I say that the functor f that I define like this, so f of a equals 1 plus a g of a. First of all, I need to show that this has a functor instance, given that g has one. So that is straightforward. I need to do this option map and so on. And I do the same with deflate. So if G has a filterable and functor instance, then I produce a new evidence for filterable instance for the type lambda, which is this. And the code is simple. Because of the signature of Flatten, it's an option of option A, G of option A, and I'm supposed to return option of A, G of A. So I just map on the option and flatten and, deflate. Cannot flatten here, I have to deflate, because deflate is an arbitrary functor G. And then I use flat map on the option, because this is an option type, so I use the standard flat map on it. So that's basically it. And let me see what was changed here. I'm not sure what was changed. I'll check it after the recording, just to make sure that everything compiles. If I find anything, I'll make a patch and upload it. The next example is the recursive construction, where you define a new functor recursively using an already existing filterable functor G, and you're adding a new data item and again an instance of a recursive functor. So this is like a list, except in the list this would be a unit, and now here we put, well, unit is filterable trivially. Now we put an arbitrary filterable here. So an interesting thing about deriving this law is that the proof must be inductive, because the type is recursive. So given a function f from a to 1 plus b, we have the fmap opt for the filterable functor g, so we have that. And also we have fmap opt for f, which is the inductive assumption. So I use the prime here to show that this fmap opt is not the one we are going to define, but it's the one that we already assume to exist and to satisfy the laws in the previous inductive step. So this is the inductive assumption. That's how we're going to derive the laws. We're going to say, if this fmap opt is already satisfying the laws, then we only use it when we call the recursive fmap opt in the definition of this functor, filterable functor. And so when we use the recursive call, we're allowed to use this recursive definition, which already is assumed to satisfy all laws. But then we prove that the definition of the next step satisfies the laws. So here's the definition. We define fmap opt by, first of all, looking at f of a. So first of all, if we're in the queue, then we just return if we're on the left side of this disjunction, we just return the fmapOpt_g applied to this. So there's not much to do. If we are in this part of the disjunction, then we need to check whether f of a is in the left or in the right. If it's in the left, then actually we do an interesting thing. So if this does not pass the filter, then we can't return this because we don't have a value of q of type GA. We return this filtered. So we descend into the recursive instance. We discard this a, we discard, and we return this filtered, this p, filtered using the recursive instance of fmapOpt. So we call ourselves, this function that we're defining now on this p, and we return the result. Why is this valid? It's because the type is recursive. So when we return that, that will be of type fb, and that's exactly what we're supposed to return, because this type is the same as this entire type. This entire disjunction is the same as this. So we are allowed to return it in the call. Otherwise, so if f of a is some b in the right side, then we return this b times, again, the recursive filter result of this. So we can return the right-hand side of this disjunction, which is fine. We can return the left-hand side of this disjunction, if we have a q, or we can return only this piece after filtering, because the type of this piece is the same as the entire type by the recursive definition. So this is a definition of fmapOpt of f. Let me show you the code to perhaps make it more clear how the recursive thing works. So here is a definition of this construction using the type constructor C6. It's parameterized by a filterable functor G and a type A. So then you have this disjunction. So this is this disjunction. The left side has a GA, and the right side has a product of A and FA, which is itself of the same type C6. So this defines this construction. So now we have a convenient place to put all the implicits for this type. And the Scala allows you to have an object with the same name as a type constructor. And if you put implicits into that object, then whenever you use the type constructor, these implicits are visible. You don't have to include them yourself or import them yourself. That's very convenient. That saves you typing and looking for where these implicits must be. And so here we put the functor instance, assuming that G is a functor, and the filterable instance, assuming that G is both filterable and functor. Although the filterable type class requires functors, so we could have just gotten the functor evidence out of filterable evidence, but it's just for convenience to have both. And now let's look at the code. Both the functor instance and the filterable instance must be recursive because it's a recursive type. So the map function takes a C6 of GA, so a function from A to B, and returns a C6 of GB. So there are two cases. The base case, you just map the GA, which should be a functor by assumption. And note that this .map syntax is available because cat's library allows you to do this with a simple import, which I believe is just import cat's syntax functor dot underscore. So I can just use this syntax easily on anything that's declared as a functor. And the step, I have two values, x and this xfa, the recursive value of C6. So I apply f to x and I map, which is the same map here, I map recursively the function f over this thing. Same thing I have to do with deflate. I have to, well, I have a base, I can deflate that. If there's a step, that means I have two values here. Both of them are of type option, and I need to deflate the first of one and the second. So the first, if the first is not empty, it means that in this type, this A passed the test. So note that in the slide I had fmapOpt defined, but here I have Flatten defined because it's easier. But it's the same thing. I need to decide what to do when this passes the test or it doesn't. If it passes the test, I return that thing, deflated, and I deflate the other part, this part, recursively. So this is the recursive call of this to the same function. And if the A is not passing the test, if this option is empty, then I need to deflate this recursive value and return it deflated alone. So that has the same type as the entire functor, and that's why I can return it like this. So just to make a correspondence between what I have in the slides and what I have here in the code, it is easier to implement deflate, not flatten. It's easier to implement deflate than it is to implement fmapOpt or mapOption or anything like that. But it is equivalent. So all the decisions we make when we implement fmapOpt are made here exactly in the same way. We need to deflate g of option A plus option A times f of option A. So every option needs to give us a decision of how to deflate it into a non-option type. And so in our fmap definition, we had exactly the same question: how to define the result of fmapOpt when this is given or when this is given and the result of f is in the left, and so on. So then we check identity law and the composition law. So identity law is easy to check because the identity function never returns an empty option, so we're never in this case, and therefore either we are here and we return the flattened q, the deflated q, which is just the same for identity, or we're in the right and then we have A times P and then we just return the same, because the recursive instance of fmapOpt already satisfies the identity law. And so when we apply that to P, we get P, identity. So in this way, we use induction, plain mathematical induction, to show that the laws hold. The composition law holds in the same way. So we need to show that this holds. Now, if the arguments are in the left, then it's just about the laws for GA, which are holding by assumption. If the arguments are in the right, in here, then we need to look at what's happening. So we have F1 and F2, and there are 4 cases. So, well, if both of them return non-empty, then the previous proof will go through. This one, it's exactly the same. So we need to consider the cases when one of them returns non-empty. If the first one returns empty, then we are returning the recursive instance, so there's nothing more to show. The second one will never be called. So we need actually two more cases only. The first returns empty, and the first returns non-empty, but the second returns empty. So just to remind you, the composition law is assuming two arbitrary Kleisli functions, so a to 1 plus b, b to 1 plus c. And we need to show that fmapopt gives you the composition. So if the first function returns an empty option, then this also returns an empty option, because the Kleisli composition is the Boolean conjunction of the two filters. So if one of them returns empty, then both conjunction also returns empty. So then it remains to show, so we collapse this equation, because this is now 1 plus 0, so we can use that case for the right-hand side. We need to show this. And that is just the inductive assumption for fmapopt prime. So if we are always in the inductive case, we don't need to prove any further. It remains to show this case. Again, the composition is empty. So it remains to show that the fmapopt applied to this and is equal to fmapopt prime, because we are in the case of 1 plus 0, so there's nothing else to do. And we rewrite this, and we again get just the inductive assumption. So this being equal to this. So this filter is really list-like. If this is empty, we go into the nested data structure. So if you expand this recursive type, it looks like GA plus A times open parenthesis, GA plus A times open another parenthesis, and so on and so on. So it's then expanded into GA plus A times GA plus A times A times GA, and so on. So if one A is empty, you can always delete it, and you are still in a disjunction. It just, you recurse into the nested FA, and you're still in the disjunction. So this is exactly like filter on a list. The final worked example is this one. This is a bit interesting. So here's what we have. We have a big type expression. How can we show that this is filterable or that it is not? It looks like a lot of work. You have to write a lot of code and then check laws, and what if you implement it and then laws don't hold? Where did you make a mistake? All that is a lot of work. So instead of trying to do that, we will analyze the structure of this data type and use these constructions, the constructions that are listed here. And try to see if we can decompose this type expression into these constructions. So let's look at it. So first of all, we have this int times string going to this big thing. Okay, let's denote int times string going to A. Let's denote this by R1A. And also we have this int going to big expression. So let's call this R2A, int going to A. Then we have 1 plus int of A, int times A plus int times 1 plus A. So there's this big piece, and after that big piece is this function type. So the function type contains that. So now we can rewrite it like that. So it's R1 applied to the type GA plus R2 applied to HA. So that's great. GA is filterable by, so what is GA is this. It is filterable because it is type 1 plus A times something. Right, we can make this A, we can put it outside brackets, and then you have 1 plus A times int plus 1 plus A. So int plus 1 plus A is, let's call it K. And that is filterable because it's of the form 1 plus A plus constant. And that gives us filterable by constructions 1 and 3. So constant is construction 1, and the construction 3 is the sum of two filterables. So constant is filterable, and 1 plus A is option filterable, of course. So therefore K is filterable, therefore this is filterable. H is filterable by the same construction 5 again, because 1 plus A times string is filterable by constructions 5 and 1. So we can see this is constant, so it's filterable. Then it's 1 plus A times filterable, which is construction 5. This is again construction 5. So H is filterable, G is filterable. And then we have, so R2 of HA is a composition of two functors. So it's a composition of functor R2, which is this, and filterable. So that's filterable. Then we have a sum of filterable and filterable. Therefore, this is filterable. And then we have a composition of a functor. Doesn't have to be filterable in that construction. And the filterable. So that's all. We just looked at the types and we use this. See, in this construction, the functor does not have to be filterable outside. So this doesn't have to be filterable. This doesn't have to be filterable. These functors are just whatever functors we want. This is filterable and this is filterable, and we're done. So we have shown, and also of course each construction comes with specific code that you can use to implement the filterables, and so you don't have to worry about it anymore. You can just follow these constructions. You can write general library that will implement all of these constructions as implicits, and you just call functions from this library. You want something, you get it. And implicits will be found automatically. So one important comment at this point is that, first of all, these constructions are not the only ones available. And second, there's more than one way of implementing the filterable. Certainly, this is a valid way, but there are alternatives, and certain applications might require different alternatives. So if you remember the examples from the previous, the part 1 of this tutorial, there are different business requirements that might lead you to different implementations of the filterable, and so you can probably add more rules, more constructions to this list, but in any case, it shows you a large number of possible functors that can have filterable behavior, and a large number of different filterable behaviors, such as greedy or collapsible or list-like filterable behaviors. So you can combine them in any way you want using these constructions. Here are some exercises for you to follow what we did in the worked examples. And finally, some bonus about filterable contrafunctors. So up until now, we were dealing only with filterable functors, but actually, filterable contrafunctors also are interesting and could be useful. And let me just conclude this tutorial with a discussion of filterable contrafunctors. And the discussion will be, again, modeled after the way we dealt with filterable functors. First of all, what are the definitions and laws? How do you define filterable contrafunctors? So the filter functions have the same signature for contrafunctors and for functors. There's, instead of deflate, there's inflate, which goes the opposite way. And instead of fmapOpt, there's contra fmapOpt, which also goes in the opposite way. So again, this is a kind of a twisted function type that has, first of all, it has reversed direction, so b to a, and here is a to b, as appropriate for a contrafunctor. But also it has this twist with the Kleisli opt category, just like the fmapOpt. All these functions are computationally equivalent. You can express each of them through any other. So, for example, filter through inflate. Contra fmap is standard for contrafunctor. So if you have contrafunctor, you can express filter through inflate, inflate through filter, contra fmapOpt through inflate, inflate through contra fmapOpt, in very much the same way as we expressed them for functors. They have different laws. 4 laws for filter, 3 laws for inflate, 2 laws for contra fmapOpt. And as before, contra fmapOpt is just kind of a twisted lifting. What are examples of filterable contrafunctors? So here are some. From A to 1 plus z, where z is a fixed constant type. From 1 plus a to z, where again z is any constant type. What is a non-filterable contrafunctor? For example, this, where f is whatever. You cannot implement inflate for it, because to implement inflate, you would have to transform this into a c of 1 plus a, which means a function that consumes, you see, ca is a function that consumes a and other stuff. c1 plus a is a function that consumes 1 plus a and other stuff. To construct that function, it means that you should be able to consume 1, that is a unit, and go on, and other stuff, and go on. But you don't have that. You only have a function that consumes a and other stuff. So you're required to consume a. You cannot implement inflate. So this gives us some intuition about what filterable contrafunctors do. First of all, let's recall the main visual image of what functors and contrafunctors do. Functors hold data. Functor f of a, in some sense, it holds data of type A and allows you to manipulate that data. Contrafunctor ca, in some sense, it consumes data of type A. It does not actually have any data of type A inside, it consumes it. Like these examples, it's a function that consumes data of type A or some other type related to A. So a contrafunctor wants you to give it one or more items of type A, and then it will consume them and give you something else, which is not A. A filterable contrafunctor is able to consume fewer data items of type A. If you filter a contrafunctor by a condition, it means you prevent it from consuming some data that does not pass a test. In other words, let's say it's such a consumer that it is able to consume less. It is able to refrain from consuming certain items. A function of this type, let's take a simpler example, a to z. with this arbitrary functor being just unit. A to z is a function that requires you to give it an a. It cannot refrain from consuming an a. There's no way for it to not consume an a. This function, on the other hand, can do it. If you don't give it an a, there's this part of the disjunction, and the function can take that and produce a z. So this contrafunctor is able to refrain from consuming certain values and still give you the result. But this functor is not able to do that. And so this contrafunctor is not filterable for this reason. So this is the interpretation, that it can consume fewer data items if necessary by filtering them out. And the easiest function, again, is inflate. So consider that function and try to implement it. Here are some constructions, some analogous to filterable functor constructions. First of all, the constant contrafunctor with identity filter. Then the functor constructions, which are exactly analogous to functor. You don't need to check any laws, therefore, really. If GA and HA are filterable contrafunctors, then their product is filterable contrafunctor. Their sum and the composition like this is a filterable contrafunctor. And here you have different combinations. You can have a functor of a contrafunctor. You could have a contrafunctor of a functor. Or you could have contrafunctor of contrafunctor. The result would be a functor, again filterable. You can do this, of course. If they're both filterable, this is a functor, this is a contrafunctor, then the contravariance is here on the left. Covariance is on the left of the arrow, so it becomes contravariant. And so this is a contrafunctor. If they're both filterable, and this is also filterable, that is quite easy to show all of this. It's just analogous because the laws are the functor laws. It's just a twist, and the twist is irrelevant for these constructions. The twist just remains the same in all computations. So whatever twist you have on the type, the proofs remain the same for the functor construction. Now there are special constructions where you have to deal with the twisted type. I will not go through the proofs of these, but just to mention two of them. So if you have this type, then you can filter, because you can refrain from consuming this A, because you have the unit. You can consume unit. And here, you cannot refrain from consuming A, but if there are no A's given, you can return 1. You can always return 1. How do you filter a contrafunctor? Well, you just give it, before you give it the data, you filter it out. So you give it less data. And the contrafunctor should be able to handle that if it is filterable. It should be able to consume less data. So that's the intuition behind it, and I'm not going to go a lot into detail for contrafunctors because so far I haven't seen a lot of obvious applications for them, but certainly there might be some. This concludes Chapter 6 of the Functional Programming tutorial.